In this lesson, we're going to be solving logarithmic equations. And in order to solve logarithmic equations, we need our inverse properties of logarithms. Two of these, we should already be slightly familiar with. These first two, we should kind of already have seen before. And the reason we look at those first two by themselves is because they're useful by themselves. The one that we're going to focus on today is this last one. This is our third and final inverse property of logarithms. And this one in and of itself is not very useful, okay? It doesn't stand alone like the other two do. Really, this last one is only used when we're solving logarithmic equations, the only place that it really makes sense. And so that's the one we're going to use today. But as we look at these, you should hopefully see the similarities as to what's happening here. Like in this one, what's happening is log base b and b raised to a power are canceling each other out. In other words, I have a logarithm and an exponential function. So here's my logarithm, here's the exponential function. And when a logarithm and an exponential function collide, they cancel each other out. And the same thing is happening in this one. I've got an exponential function, see something raised to a power, but then I also have a logarithmic function. And when I have a logarithmic function and an exponential function that have the same base, they cancel each other out. So really it's the same property, but in the reverse. When we look at this guy, here the logarithm is canceling out the exponential function. Here the exponential function is canceling out the logarithm, okay? So really it's the same property, but written in a different order, all right? But this, again, this third one is the one we're really going to use today, all right? So what we do when we solve logarithmic equations, we're going to rewrite each side of the equation as one logarithm. We got to condense this thing down to a single logarithm on each side. Then we're going to undo the logarithm using the inverse properties, specifically that last inverse property to cancel out the logarithm. And then we're going to solve what's left. Okay, so again, we're going to rewrite it as a single logarithm. We're going to do that using properties of logarithm. Addition of two logarithms becomes multiplication inside the logarithm. Subtraction becomes division inside the logarithm. Multiplication becomes an exponent inside the logarithm. That kind of stuff, all right? We rewrite it so it's one logarithm. Then we're going to undo using that last property that's listed here. Then we're going to solve what's left, okay? For example, when I look at something like this guy, right now there's more than one logarithm on the first side of this equation, so I have to rewrite it. So addition I can rewrite as one logarithm, and I multiply inside the logarithm. So this becomes log base 2 of 7x. Now it's all written as one logarithm, so from here I can use that property to undo some things. And it might be difficult to see, but as we start to think about this, we want to use this property, and so the question becomes, how do I use this property to cancel out the logarithms? Okay, and it's very difficult to see when you first look at this, but here's essentially what we're going to do. We're essentially going to take each side of the equation and make it an exponent. So I'm going to do log base 2 of 7x as an exponent. Over here I'm going to do log base 2 of 35 as an exponent. And the base that I'm going to use is 2. Alright, so I'm going to do 2 raised to the power equals 2 raised to the power. So each side of my equation becomes an exponent. And I use 2 as the base of my exponential function because I know that log base 2 and the 2 cancel out. See, what's going to happen here now is I have this rule that says log base 2 and 2 raised to a power cancel each other out. Log base 2 and 2 raised to a power cancel each other out. All right, and the shorthand that I like to use for this is I just do this. I say, okay, on this side I do 2 raised to this power, on this side I do 2 raised to this power, and then I cancel. The log base 2 and the 2 cancel, log base 2 and the 2 cancel. And the reason I choose 2, the reason I don't do 3 is because if I did 3 raised to the power of log base 2 of 7x, well, nothing would cancel out, and that would be kind of useless for me. All right, so in order to use this rule, I essentially do 2 raised to the power of each side. All right, I make each side of the equation an exponent, and then I use the base and the fact that I have an exponential function now to cancel out the logarithm. All right, when those things cancel, over here what I'm left with is the 7x. Over here what I'm left with is the 35, and now I can finish solving this thing by dividing by 7. Okay. If I look at the next one, again, if I follow the same basic rules here, what I'm going to do here is I'm going to write this as log base 3 of a 5x squared. Addition becomes multiplication. Over here, this is already written as one logarithm. And now from here, I'm going to do 3 raised to the power of each side. So I do 3 raised to this power equals 3 raised to this power. Each side of my equation becomes an exponent now. And what happens is log base 3 and 3 raised to a power cancel out. Same thing over here. So it leaves me with a 5x squared equals 15. Now from here I'm going to go ahead and finish solving this thing. I divide by the 5. That leaves me with an x squared equals 3. I was about to get a little ahead of myself. And now I take the square root of each side. When I do that, I'm left with x equals plus or minus the square root of 3. And the interesting thing about logarithms, what we should do is really plug these things back in to check them. And what you're going to find out as you start plugging these things back in to check them is that you can't plug a negative into a logarithm. Anytime you try to plug a negative into a logarithm, it's going to give you an error message on your calculator because there's going to be a little bit of a conflict here in terms of the values we're allowed to use in terms of the domain. We can't plug negatives into this, so basically any negative answer that we get is going to be an extraneous solution. So the negative doesn't work, so I'm only going to use the positive square root of 3. Alright? And I didn't mention that in the previous one because, well, x equals 5 is a valid solution. Had it been x equals negative 5, then it would be no solution. Okay? So again, can't plug negatives into the logarithm. Here, if I do the same thing, again, I'm going to combine these. Addition becomes multiplication inside the logarithm. So when I do x plus 1 times an x minus 3, it gives me an x squared minus 2x minus 3. And you can take that off to the side and FOIL it if you want to. You got to do the x plus 1 times the x minus 3, so you have to FOIL, distribute, that kind of stuff. Now to undo log base 7, I do 7 raised to the power of each side. So I do 7 raised to this power equals 7 raised to that power. And now the log base 7 and 7 raised to a power cancel each other out. Same thing over here. So I'm left with an x squared minus 2x minus 3 equals 5. Now I have a quadratic to solve. In order to solve quadratics, I've got to get everything on the same side, so I'm going to subtract the 5 from each side. Now I'm going to build a bridge and solve by factoring. So in this one I build a bridge. The two numbers, it's going to be an x minus 4 and an x plus 2. I set each factor equal to 0, and I solve each. So I end up with two answers here. I get x equals 4, I get x equals a negative 2. But again, as soon as I try to plug these back in, I'm going to find out that that negative 2 is not going to work because it's going to give me a negative inside the logarithm, and that's not going to, it just doesn't work when I try to plug it back in. So the only answer I get here is x equals 4. And that's it. If I look at the next one, again, combine these. Subtraction becomes division, so it becomes log base 3 of. Well, 24x divided by 6 is a 4x. Now to undo log base 3, I do 3 raised to the power of each side. Log base 3 and the 3 cancel out. So I end up with 4x equals an 8. I divide each side by the 4. So I find out that x equals 2, and that is a valid solution. I plug it back in, I find out that it works. Okay? Same thing with the next one. Subtraction becomes division inside the logarithm, so this is going to be log base 5 of 7 over x when I divide. And now to undo log base 5, I have to do 5 raised to the power of each side, so I do 5 raised to this power equals 5 raised to this power. The log base 5 and the 5's cancel. So I'm left with 7 over x equals 10. And probably the easiest way to finish solving this one, keep in mind this is like a 10 over 1, I would cross multiply. So I do 10 times the x gives me a 10x. I do 7 times the 1 gives me a 7. And now I divide each side by the 10. So I find out that x equals a 7/10. And that's an okay solution. Okay? If I look at the next one, again, properties of logarithms, I got to rewrite this as one logarithm. So over here I have multiplication. Remember, multiplication becomes an exponent inside the logarithm, so I bring that up as an exponent. So this is going to be a log base 7 of x squared. Now to undo log base 7, I do 7 raised to the power of each side. So I do 7 raised to this power equals 7 raised to this power. The log base 7's and the 7's cancel out. So I'm left with x squared equals x plus 2. Again, this is a quadratic, so I want to get everything on the same side of the equation, so I'm going to subtract the x and the 2 from each side. So I end up with x squared minus x minus 2 equals 0. And I'm just going to solve by factoring. So I build a bridge. This is going to factor into an x minus 2 and an x plus 1. I set each factor equal to 0. And now I solve each, and it looks like I ran out of room here. When I solve each of these, it gives me x equals a 2 and x equals a negative 1. But of course, the negative 1 is an extraneous solution. It's not going to work. So it's just the 2. Okay? And so now the question becomes, as you start to look at these and realize that when I have the same logarithm on each side, really it's the things inside the logarithms are just equal to each other. That is a shortcut that you can use when you have the same logarithm on each side. When you look at these, like here it's the 4x equals the 8. Here's the 7 over x equals the 10. Here it was the x squared equals the x plus 2. That only happens because we have the same logarithm on each side. The reason that we show that step of 7 raised to the power of each side or 5 raised to the power of each side is because of an example like this. When I look at this guy, again, these guys go up as exponents. So what I'm left with here when I do that is a log base 2 of x to the second minus log base 2 of 9. And now subtraction becomes division inside the logarithm, so it becomes log base 2 of x squared over 9 equals 4. And now from here, I don't have the same logarithm on each side, and this is where this rule is really helpful. To undo log base 2, I do 2 raised to the power of each side. So on one side, the log base 2 and the 2's cancel, so it leaves me with an x squared over 9. On the other side, it leaves me with 2 to the 4th power, and 2 to the 4th power is actually a 16. Okay? And so now from here you would multiply each side by the 9 and finish solving for x. Okay? So that gives me an x squared equals 144. I take the square root of each side and I find out that x equals plus or minus 12. But of course the negative answer is no good, so I toss it and just get x equals 12. Okay? So again, it's important to understand why the things inside the logarithm equal to one another. It's because you're undoing the logarithms in this way. All right? And when you have just a number over there, you can't use that shortcut, okay? Same thing with the next one. I'm going to combine these. Addition becomes multiplication, so it becomes log base 3 of, that's going to be an x squared plus 6x when I distribute. And now to undo log base 3, I do 3 raised to the power of each side. On one side, the log base 3 and the 3 cancel, so it leaves me with an x squared plus 6x. On the other side, I have 3 to the 3rd power, which is 27. And now I subtract the 27 and I solve the quadratic, and I'm going to solve this by factoring. Okay? So I build a bridge. This is going to factor into an x plus 9 and an x minus 3. And now I set each factor equal to 0. And solve each. And of course, I've got to check these answers. Remember, the negative answers aren't going to work. So as I solve each of these, I'm going to find out that only one of these answers works, and it's the x equals 3. Okay? The negative 9 has to get tossed because I can't plug that negative back into the logarithm. All right? So again, when you're doing these, use your properties of logarithms to rewrite each side as one single logarithm. Then undo the logarithm by doing the appropriate base raised to the power of each side using that last inverse property logarithms. Then solve what's left. Okay? And then always check your solutions. Make sure you get rid of any extraneous solutions. In particular, negative answers. Negative values can't be plugged into the logarithm. Okay?